We are honored to have here Fanny Bouton, Quantum Lead and Product Manager at OVHcloud, to address the topic why quantum computing is still relevant alongside AI. So please welcome Fanny Bouton.
Hello everyone. Can you hear me correctly? Yes. Okay, I try to be short because we have a lunch that my company paid and it's important that you have time to eat. And I try to respect that. I know it's important in Italy. Okay, I'm talking about quantum today, quantum technology. I'm Fanny Bouton, he said that, and I'm quantum lead at OVHcloud. Just to remind you, what is OVHcloud? OVHcloud is a leader in cloud in Europe. It's like either AWS or Google, but it's a French company, and it's in Europe, and it's GDPR. We are 3,000 in the world, and we have 43 data centers around the planet. It's an international company, and we have a lot of things with AI, and you can work with us if you are interested. Don't hesitate to talk with my colleague in the room. It was just to introduce you if you don't know us, because sometimes in Italy, I know it's not so recognized. To tell you why I talk about quantum today, I start to discover that in comics in the 80s, and computing was all the part of my life. This is my first computer. It was the ECL 1501, and I learned to code on that when I was 6. My father was in computing. And all my life was about that. And in '96, a friend I have in a newspaper, a news about we can have a teleportation of atom. And I'm fan of science fiction because I read comics, and I'm also fan of Star Wars. And I say, oh, cool, quantum is nice. And in 17, another friend comes to me and say, do you understand quantum? And say, no, it's really a research thing, it's really complex. And say, okay, can we do a vulgarization conference? During 20 years, I was journalist, tech journalist. I was going on CES, on Mobile World Congress, and I talk a lot about technology, and I decided to vulgarize quantum computing. I didn't expect what's happened after, because it's an amazing world. And for the mind who want to discover what is the future, for me, it was definitely the thing, but I'm not alone about that. And I met the first people I interviewed, it's Alain Aspect, and now he's a Nobel Prize of Physics, and he proved the entanglement. And we decided at OVHcloud, when I start to work on startup in 2020, to do a special program about quantum computing. I continue. I'm also a fan of Formula One. And I think what is important, it's for few people, they ask me when we have the faster computer in the world, and the quantum computers may be like a Ferrari. Imagine it's a Ferrari. I tried to say that correctly in Italian, but sorry if I didn't do. What I tell you today is the story. It's where are we and where are we going? And you will see the Formula One is not today. What is to be quantum? This is the first question. It's to understand that we use new law of physics, and the quantum particles, it can be photons, atoms, have a different specificity. There is a quantization. An atom can be to have different level at the same time of energy. It can be the duality wave particles that electrons, photons, and atoms have. They can be the both at the same time in the quantum physics. They have the superpositions, and the more weirdest but interesting one is this is the entanglement. If you entangle two atoms or two photons and you separate them at 2 kilometers or 10,000 kilometers, this is if you do something on one, the exact same thing happens to the other. What is interesting is Alain Aspect, the Nobel Prize that I met, is proved that in '94, with this, and this is why he has this Nobel Prize. We don't know how to entangle atoms or photons, but we don't know what's happened in that, and it's really interesting. If someone tell you you know how to what's happened in entanglement, he is a liar, because even the Nobel Prize don't understand. He know how to do, but what's happened, we don't know. It's a bit magic. What is important also to understand is there is two waves and two revolutions about quantum. The first one, it was to discover these small particles. And it's what's happened in a transistor, in your TV with LED. Photons are quantum particles. If you have a quantum TV, it's because there is photons inside. It's not because there is a quantum chipset inside. It's not wrong, it's marketing, but it's important. And in the 47th year, we discover and we know how to watch and manipulate these small particles. The second revolution, it's when Alain Aspect discovered how to manipulate them and how we can manipulate several particles at the same time. And this is the second revolution of quantum, and this is where we can find how to create quantum computers. What is the quantum computing promise? It's to resolve exponential problems in a reasonable time. Even problems that we can't solve in a classical computing, even in a HPC. It's not replace a classical computer. It's new type of GPU. It's a new powerful to optimization, simulation, engineering, and maybe a bit, and you can be interesting, optimize the learning of the machine learning. And it's why it's interesting. The other things, and why a lot of people working on quantum computers, it's because we know with the low Moore that we're arriving at the end of a power of the classical computing and need to find how to accelerate things that we can't resolve today. And sometimes a lot of people tell me, yeah, but we know to do that really faster now. Yes, but we have so many complex things to imagine and to resolve always, and it's why it's really interesting. And if people ask you, what is the best field for, what is it? It's better for finance or for health? This is, in general, what's happened. I can tell you, no, it's in all the field of industry. You can find optimization and simulation. It's really important to understand that too. It can be powerful for every sectors. You have difficult type of problem, and what is interesting, it's also to understand. This is just this part of problems that we can solve. You can do in the future video games or music or anything like that on quantum computers. It's really for this type of problem. It's really for exponential problem, and you have few examples on this slide. Another part, it's to understand that we have different parts. At this point, we have NISQ computer. It's small quantum computer. Quantum computer exists, but we can do small things, and we don't have an advantage of on classical computing. But in the future, with FTQC, and it's using gate-based full quantum computers, and it's in a long time, we can resolve more complex things. And when we do protein folding or protein interaction, for example, we can imagine really nice drugs, but we can also solve other really complex problems. For the people who want to know when we have the quantum computer, the things. First things, I would like to remind you, 30 years ago, I had 21, and I doing FX on classical computer. my computer was 486 DX36 computer. It was only 40 megabytes on my hard drive. And I imagine I buy a ticket to go to see The Mask, the first FX movie in US, because it was I don't want to wait 9 months because we wait at this point and we don't have a movie at the same time on all the planet. And I imagine one day I have a movie with everyone is in FX. It's 30 years after, and I'm really happy to see that. And 30 years, it's really fast. Maybe you are young and you imagine it's in a long time, but it's arriving so fast that you imagine. Enjoy your life. It's really important. For the quantum computers, maybe it's in 30 years, but I hope I will be alive. But you have different paths, and what is interesting is you can start to do things even if we don't have the powerful computer. I did FX on 40 hard drive megabytes, and it's really important to understand that too. Where we are here at the beginning of Ferrari. It's really slow. But it's a car. It can go on the track, and we need to do a lot of things on that machine. For understand how it works and how we use the qubits. The qubits, it's a unit. It's replaced the bits that you have in a classical computer, but it can be 0 and 1 at the same time. If you want to be shorter and don't to go too much in science, it's to have 2 states on the quantum object. You can represent that scientifically like a Bloch sphere representation, and we use the angle and to see where is the 0 and the 1, and what it's moving really fast or have this different position at the same time. You have the 0 and the 1, and it's going mathematically exponential about the results. For people who want to deep dive in the science, it can be like Death Stars in Star Wars. It can be killing your brain. Don't think too much to understand quantum. Sometimes put your brain in the back and just try to develop. But if you want to understand more, it's really different that you're doing today. You can't evaluable correctly. You can't copy data with quantum computer. We don't have quantum memory. You don't have a non-individually erasable possibility. And it's a probabilistic results and say, okay, what I'm doing here and how I can compute with that. We can. The goal is the possibility to do a lot of same probability at the same time and have the tendencies of the results, and it gives you the results. It's not to have a determinist. It's not yes or no. It's a probability. Other things, it's running differently, and it's why you need to learn a new type of code. We don't program with the same language and at the same way than on a classical computer. For example, you can see the classical gates that you know today. The quantum gates, in general, it depends the type of quantum computer, but you move the door around the qubit, and it's not the qubit moving inside the transistor. It's different. And to see the different type of the door and how we move around that, you can imagine the Bloch sphere like that. Like I said, it's new programming model, and it's really important to understand that. You have script Python code to go in framework, and you have emulators to work on these quantum computers. But at this point, and I explain why, you have, for each type of quantum computer, a type of code to do. And it's like always like a Formula One. There is so many different cars, but they don't use the same petrol, the same pilot, the same team, and the same wheel. And you need to learn for each how it works. Why? Why is that? Because you have main qubit type. There is 7 type of qubits, 7 family. And inside this 7 family, you have a subpart of, and it's 10 particles. Few use photons, few use atoms, others use silicons, or even a few using cat qubits. Yeah, it's, it's existing. What is interesting is that it's because we are at the beginning of the new computing. If you go back in the past, now we know that in our phone, in every what we're using, it's silicons to do a transistor. But at the beginning, we start to do 0 and 1 with water, with lamp, with a lot of materials. And one day, we find that it was industriable on the silicon. It was maybe not the best, but the most ratio performance, cost, and price. And it's what's happened today. We don't know what is the best type of materials to do qubits. And what you see in this whole logo, it's, this is the number of companies and research labs working in the world to do quantum computing. And it's like in Star Wars, it's to have a race pod and a different type of pilot and find where is the best one and where we can go in. What is interesting is we are really good in Europe. We have a lot of good machines and we have a lot of good pilots. And we have the 10 type of qubits in Europe and they are developing. And Cocorico, for French, we have 6 of these in France and it's really important for all the Europe. One of the challenges is the scalability. Few of the qubits are really stable. We can scale them with difficulty. And for the other one, it's difficult to scale them, but they are really stable. And what we need is a qubit who can't move. They can't move. They can be in a long time, the most longer time, to put the algorithm inside the quantum computers, and it don't, and the calculation don't fall. It's also a difference. And the goal is to find good qubits, really stable, who don't move and don't have a good consumption energy, and we can scale a lot. At this point, the better quantum computers have around 100 qubits. The best one is IBM today. But tomorrow it can be another one. Pascal or IQM, the Finland company, are really close to them. And I can explain why it's complicated, for example, for IBM. Do you know that? What is it? Yes? Who already sees that, this type of image? Not so much, but this is inside a quantum computer of IBM, and a few others are like that. This is just the part of to refrigerate. It's really cold. It's few Kelvin. It's more cold than the space. And I just tried to show you, but the chipset is just here. This is all the fridge, and all the wires are just to pilot this chipset. And it's really interesting. Because the quantum computer to the labs, it's like that on the left. And on the right, this is what they sold. It's 100 qubit computers. The Italian part of that is it's an Italian designer for coffee machines who do the design of these machines, and they sold around the world. And they put all their communication about that, more than the power of the machines. But it's really important. You have really good designers. Because if you see the other, they don't use the Italian designer, and the D-Wave Canadian machine is more classical. The IonQ US one, same, is, and the Pascal, the French one, is biggest also. But this is what is a quantum computer. It's not so sexy when it's not open. It's what's inside is nice. And for to go inside the quantum computers. What you can see at the center, this is the famous chamber with you see with the chipset, but it's complicated. You need a compressor to put with helium-4 to refrigerate, and you need also a qubit controller and a lot of wired. And imagine you need 2 wired per qubit. Actually, it's okay, it's unstable, but if you want millions of wired to pilot the qubits, it's complicated. And it's why maybe IBM can be stuck really soon. They need to find other engineering to pilot the qubits and scale. And it's more easy for other type of qubits. And you need a classical computer to enter what's happened in the algorithms and to keep the results of the quantum computers. Like I said, you can't replace classical computing. It's just a big new type of GPU. What is interesting also is to understand what is the difference. The both HPC and quantum computing can do the same things. What is in gray, it's only HPC can do that. But in clear blue, it's only quantum computing can do and never classical computing can do, because of the mathematics and the type of algorithms. And quantum physics simulation, high combinatory complexity problem solving, and relatively small data, because you can't use big data in quantum computers. It's really important also to understand that when you start to code. What is important also, it is to have a team play. It's really important to have the car. And if you have a Formula One, it's okay, but the first thing is you need to learn to drive, and I think Charles Leclerc started in a kart, and what we have now is kart. We can start to drive, but you need to have the developers, it's the guy who puts the wheel, everything is important, and each part of the details for to go on the quantum race is important. And now we need to have engineers, developers, physical guys, mathematicians who work together to prepare what's happened on the Formula One of quantum computing. It's like, imagine if an iPhone or a smartphone with the power what they have will be sold, but they don't have OS and apps. It's not useful. You need to be prepared. The other part to working in team is we are really good in Europe, and it's really interesting to see that we can be at the front of the next industrial change. We have IQM in Finland, AQT in Austria, Candela or Pascal are French. There is a startup who starts to build a quantum computer in Italy, and you have a big research center, Cineca, financed by Europe. It's really interesting what's happened in Europe, and we need to work together. It's not because France have 6 types of quantum computers, it can win the race. For the money, for the industry, we need to work together, and it's really important to understand that. And to buy and to start the research, no. Don't wait too long to start your journey in quantum if you are interested. This is a national plan. I tried to do fast on that, but what is interesting here is to see that Europe is in the 2nd position of investment if you watch all the flag. We are good on research, we are good in startup, and we are good in investment. What we miss, it's investor money. We don't have VCs and funds enough big. And how we can do the difference is that our industrials start the R&D, start to consume what the startup and the quantum research do. And with this money, we can finance the development of the European quantum development. Like I said, we have CART, and what is CART for to start your journey as a developer? It's emulators. Emulators, it's software running on CPU, classical CPU, and it's up to 20 qubits. You have the access to the interface. It's more like assembler at this point. A few companies work to do a WYSIWYG things to develop more easily at this point. But you can try to understand how to code algorithm on each type of quantum computer. And it's why it's interesting, because it's running on CPU, and it's only less €2 per hour. It's really accessible to learn quantum computing and to develop on that. And by the way, I think we have voucher for people who want to and be interesting about that. And at OVHcloud, now we have 8 emulators, and 7 are European. We have only Qiskit from the Americans, because we have a lot of demand on that. They are leader at this point, but it's interesting. One other thing, it's to imagine the future. And yes, I did this image with ChatGPT and DALL-E for to imagine the future. Can we have an AGI, a big artificial general intelligence on quantum computers? I think you understand now it's not possible. It's not for that. But you have few things. First one is to understand it's more AI at this point, help quantum computing to develop. We can resolve and to simulate and do digital twins of the chipset to understand how it works. We can use the emulation on that on classical computers. But after, you can also doing software things and work on the machine learning. I'm not too much specialized about LLM, but you have this part to develop and to train all your data. And the goal is to have smaller set of data, consume less energy on small quantum computers, and to have a part of your algorithm can go on a small quantum computers and the other part on GPUs. And we can have an advantage of what's happened on only a HPC. It's really interesting to try that and to understand. A lot of companies start this, and for example, you have Qubit Pharmaceuticals. They develop drugs, and they work on the interaction of the drugs on the cells of the body. But they work on GPU with AI, but they work also in parallel of the part of the algorithm on linear mathematics to code and to have a small advantage of the part of the algorithm. And they will be ready for the future. They prepare the algorithm for when the quantum computer with the power arrive, they can just put in the machine and they are in advance. They don't wait that the machine arrive. And you can do that with emulation. You can start to code and to work on the algorithms. And it's in medicine, but it's working on every field. The other interesting things, and if you want to build new startup and have investment, it's to find use cases, and there is only 80 algorithms actually working on quantum computers. It's to develop new algorithms and new type of software and put patent on that, and you can sold to, in the future, to big brands who have a lot of money. And there is many things to do on that. There is only 200 startups in the world about software. It's not enough about quantum computing. Like I said, if you are interested, I can send you the link about this whole paper. But it's what is machine learning on quantum computers. A lot of people work on that, but it's just the beginning. And if you want to refresh your brain, it's a big, nice challenge. I think I'm arriving closely to the end. If you are interested to deep dive more, to see use cases, to meet people about quantum, there is an event the day before Vivatech in June, the 10th June. If you want a free ticket, you can scan this QR code. It's one day, it's thousands of people come to talk about quantum, and there is developers, but also clients and researchers. And it's in Paris at Station F. And for the other who want to deep dive really, who want to sleep really fast, you have a book of more than 1,500 page, Understanding Quantum Technology. It's my friend Olivier Zrati who wrote that. It's free. You can download this whole page freely. If you prefer the version in paper, it's on Amazon, and you need to pay Amazon for the book. And if you are interested, and if you talk French, you have also podcast. This is the other QR code. And that's it. I think I'm just on time. Thank you, and don't hesitate if you have any question. I hope it was interesting for you.
Okay. Thank you, Fanny, for your talk. We have 5 minutes, and we can start with a question and see if brief.
Hey, Florian from Gina AI. Thanks a lot for your talk. We work on search, and search is a linear problem if you do it in an exhaustive way. So I would be interested in how can quantum computing improve search, and when we look at the runtime of linear, what can quantum computing actually do to improve this runtime? Will it be constant runtime? Will it be square root runtime? Or what is actually quantum computer turning our search problem into?
It's a very, very specific question and technical question. I try to give you a correct answer. Like I said, you can't use a lot of data when you use quantum computer. We need to think with small data, and for research, it can be complicated. It's to accelerate the training of this data. It's to, you can, for example, decide to have, I search my word in English also, it's more easy for me in French, but it's to go and to deep dive in all this data in an algorithm. You need to put everything in an algorithm and to send the algorithm in the quantum computers to have the best answer. I'm not sure in your field it can be really useful at this point, because it can be search a lot of words in a research, like if I understand correctly.
Okay, we have time for another question. No, we have time for another question. Okay.
So thank you for the talk. I am by training a computational chemist, so I'm really waiting for this and not to do this slowly with classical computers. So what do you think is the threshold of qubits with this really will get commercial traction? And it's true that will be a slow increase, but there will be an S-shaped curve when really there will be traction from the market. Do you have your projections where this number sits, and if you can motivate this?
So you want the number when it's starting, and what is the number of
qubits where you will start buying more and more?
Yeah. Few years ago, it was just 2 or 3 qubits, and few quantum computers are only on that. For example, Alice and Bob, it's only 12 qubits, or Candela, it's 20 qubits at this point. But they can be more powerful because they are more stable than 100 qubits of IBM. This is one of the first points. It's not the number of qubits, it's more the logical qubit, and the longer of the stability of the qubit is more important. And there is a starting about benchmarking about that. It's coming next year, and it will be really interesting to have a good comparison and stop to just compare the number of the qubit. What we can see, it's at 1,000 qubits, we will be an advantage of HPC. A big, like a Genze or Leonardo HPC, on the blue part of calculation that I showed you just before. But, for example, the Shor algorithm that a lot of people talk and who kill internet, the RSA key and the Bitcoin and the securities that we have today, It's more 1,100 of qubits, stable qubits, logical qubits, to run it. And it's in 20 or 30 years. And it's why it's interesting. It's sometimes we need to secure now the data can be attacked in 30 years, but we have time to do that also. What is interesting is to see when we have advantage about HPC, and we can combine small quantum computer and HPC also. It's working together. And after, when we have these full quantum computers, we can also continue to merge the two technology. But yeah, after there is, I'm not specialist about numbers and money, but the projections are really good. And I suppose I'm not here if it wasn't. They can't give me money to buy more quantum computers if it's not good projection. Other question?
No, I think that time
maybe one on the back,
is up.
because I finished a bit early.
Let's try.
Just one question, and after we can continue to discuss.
Thank you very much for your interesting talk. I was just wondering about quantum computation and encryption. If you can say some few words about where we are, and are we ready to be prepared for like post-quantum, era that we have a lot of, issue maybe with.
It's what I said about the Shor algorithm. It's we need a big, powerful quantum computer to run this algorithm who can attack our security at this point. What we need to imagine, it's a good mathematician arrive with a better algorithm than the Shor algorithm and can run on small quantum computer, and it can be dangerous. But at this point, it's not existing. The other point is we know how to secure with classical computing and to do different things than the RSA encryption that we have today. The goal is when we decide to do that. The NIST in US, the ANSI in France, and there is a lot of security agency who work to give what is the good way and what is the new protocols to follow around the world, because we need to be agreed that the internet is running, the new internet running on the same protocols. Follow what's happened, follow the NIST and the other agency, and you know when you need to turn. But you can't avoid, there is a change in few years, and we need to follow that because there is a threat, and we don't know when we can have the power to apply these algorithms, these dangerous algorithms. Is that clear? Okay. Thank you. I think it's time for lunch. Yeah?
Okay. Thank you very much, Fanny.